Hi, John Hess from FilmmakerIQ.com. Today, we'll dive into the history and science of lenses and how these little pieces of glass make filmmaking possible. People have been fascinated by the properties of translucent crystals and glass since antiquity, long before we understood anything about light. Now, the first lens or oldest artifact that resembled a lens is the Nimrud lens, dating back to 750 to 710 BC Assyria. The intended use of this piece of polished crystal is still a bit of a mystery. Now, perhaps it was used as a decorative stone. Perhaps it was used as a magnifying glass for making intricate engravings, or perhaps it was used as a fire starter. The ancient Greeks and Romans give us the first recorded mention of a lens in the Aristophanes play The Clouds from 424 BC, mentioning a burning glass. That's a fire-starting magnifying glass made out of water-filled glass sphere. In fact, our word lens comes from the Latin for lentil, which is shaped like a double convex lens. But these first lenses were either polished crystal or water-filled glass vessels. The idea of producing a lens purely out of glass, well, that didn't come about until the Middle Ages. And it began with this man, Abu Ali Hassan ibn al-Haytham, also known as Al-Hasan. Born in Basra in 945 AD in what is now present-day Iraq, he settled in Spain, where his ideas would found the basics of the scientific revolution, including theories on vision, optics, physics, astronomy, and mathematics. He was the first to accurately describe the eye as a receiver of light rather than an emitter of rays that the Greek scholars Ptolemy and Euclid believed. He was the first to describe the camera obscura, a pinhole camera that had been known to the Chinese but never written down. But for our story today, Al-Hasan was key for his theories on glass lenses. Now, based on his works, European monks began to fashion reading stones. Now, these are hemispherical pieces of polished glass that could be placed on top of a manuscript to make them easier to read. Now, this, you can imagine, is a godsend for monks with aging eyes. But why stop there? As glassmaking became more sophisticated, Italian glassmakers began making reading stones thinner and even light enough to wear. The first spectacles appeared in Venice between 1268 and 1300 AD. This mid-14th century fresco by Tommaso da Modena featured monks donning the trendiest and most sophisticated wearable technology of the time. But lenses weren't just for utility and fashion. They were about to be used for important scientific study. That is, being able to see things really far away and really up close. The first refracting telescopes for astronomy were built by Dutch spectacle makers in 1608 and refined by Galileo in 1609. A few years later, Galileo would alter a few elements on the telescope and create the world's first microscope. From opening up the vast cosmos with Galileo observing the moons of Jupiter to inner space, revealing to Robert Hooke the microscopic cells, furthering our understanding of biology, the lens has been both a literal and metaphorical fire starter for humanity's scientific understanding. Now, this is a good time in our story to stop and look at the science of how lenses work. And it's always a little tricky when looking at the history of science because a lot of the basic understanding we take for granted today were total mysteries to scientists back then. Now, having said that, though, let's cheat and apply some 20th century understanding to the discoveries being made by people like Willebrord Snellius, Christian Huygens, and Isaac Newton. Now, let's start with a 20th century understanding of light. We now know that light is a form of electromagnetic radiation, which also includes radio, microwaves, infrared, ultraviolet, X-ray, and gamma rays. Now, all electromagnetic radiation travels at the speed of light in a vacuum, a constant 299,792,458 meters per second, approximately 186,282 miles per second. Now, that's regardless of who the observer is, but that is the speed of light in a vacuum. When light travels through a medium, the electrons inside that medium disrupt the path of the light ray, slowing it down. The amount of slowing down is described by the material's index of refraction. The larger the index of refraction, the slower light travels through that medium. Now, air has a minuscule index of refraction, 1.000293. So for anything that's not a planetary scale, it's negligible. Water has an index of 1.33. Now, if we shine a laser through an aquarium at an angle, we can see how the slowing down of light bends the light beam as it travels through the water. Once it reaches the end of the aquarium, the light beam continues along its original angle. But if we curve the surfaces of the entrance and exit points, we can actually bend the light and direct light beams along a different path. Now, to demonstrate, I create a few homemade lenses using gel wax. Using a square piece of gel wax and a protractor, we can determine the index of refraction using Snell's law. Now, if we curve the surface into a convex shape, here a double convex lens, we can redirect the light beam. Convex lenses will bend the light inward, whereas concave lenses, here a double concave lens, will diverge light. There's only so much you can do with homemade lenses. To explore the properties of lenses, we stepped up our experiments with real glass lenses and a visit to YouTube Space in Los Angeles. The first and most important part of a single lens is the focal length. The focal length is the distance from the lens to the point where collimated light rays, that's parallel light rays, where those light rays converge. You can think of collimated light as light coming from a very far away point in space, like the sun. Using a pair of laser pointers and some fog, we can see that this convex lens has a focal length of 130 millimeters. Now, for determining the focal length of a concave lens, we would continue the diverging lines backwards. This double concave lens has a focal length of 125 millimeters. So, now let's talk about how we get a real focused image using a single lens. When the object we're trying to focus on is very far away, we're dealing with collimated light rays. So in order to get a focused image, we would need our imaging sensor, the imaging plane, at the focal length. But not all light rays are collimated. Light radiates from an object in a spherical fashion, and the closer you are to something, the more divergent the light rays. So how does a lens focus on light from an object that's close? Well, to solve this question, we have the thin lens equation. 1 divided by distance to the object plus 1 over distance to the imaging plane equals 1 over the focal length. Well, first off, let's talk about a really far away object. As the distance to the object approaches infinity, as it gets bigger and bigger, the 1 over the distance to the object, the inverse of that, approaches 0, leaving us a little algebra, and the distance to the image plane equals the focal length. So far, so good, but let's try to focus on something closer. Don't worry, we won't get too crazy with the math. In fact, it's actually easier to visualize with some lenses and a couple laser pointers to do some lens ray tracing. We'll fire our first laser perpendicular to the lens. Once it hits the lens, it will bend toward the focal point on the far side of the lens. Now we'll fire our second laser, this time aiming toward the focal point in front of the lens, so that when it hits the lens, it will be bent and exit the lens in a perpendicular angle. Where the lasers first meet in front of the lens is our object distance. And where the lasers converge behind the lens is where our focused image will be. So in this first example, our object distance is 260 millimeters. And our focused imaging plane will also be at 260 millimeters using a 130 millimeter lens. Now notice how both distances are exactly 2 times the focal length, and the math does indeed check out. Let's try another example, this time with the object distance at 340 millimeters. Now using the same 130 millimeter lens, the focus image will be at 210 millimeters. Now notice how the beams converge beneath their origin. This means that the image created will be upside down. Laser ray tracing can be a little bit abstract, so let's try it with a light bulb as our object and a piece of paper as our imaging sensor. Putting the light bulb at 340 millimeters in front of the lens and the paper at 210 millimeters behind the lens does indeed yield a real focused image. Notice how the shape of the light bulb filament is upside down in our projected image. And if we move our imaging plane closer and further away, we will see the image go in and out of focus. Now, this works for a single thin lens with an object distance of about 2 times the focal length or thereabouts. As the object distance gets closer to 1 times the focal length, the imaging plane approaches infinity, sort of the reverse of what happened when we talked about collimated light. But what happens when the object is inside, less than 1 focal length? Well, the answer to that is we'll have a negative image distance. It's hard to simulate with my experiment design here, but what you'll notice here is the light never comes to focus past the lens. Instead, it looks like it's even more divergent than when it started. Let's use a diagram to make this easier to see. Once again, one ray perpendicular to the lens which bends to the focal point on the far side of the lens. And the second ray coming from the focal point in front of the lens through the lens to create a perpendicular ray. Now the key here is our eyes and our brain don't know that light is being bent by the lens. We assume that all light rays are straight and continuous. So if we follow the light rays back from the lens, we end up constructing a virtual image behind the object, right side up and magnified. This is how magnifying glasses work. The real fun occurs when we bring more than one lens into the mix. Now, telescopes use objective lenses with long focal length and an eyepiece lens for focusing. The lenses have to be placed inside the focal length in order to work. The microscope switches out that objective lens with a long focal length for a lens with a very short focal length. Combining multiple lenses also allows us to change the magnification. Here's a model of an afocal zoom lens using 2 convex lenses with a concave lens in between. As we move the concave lens, we can change the distance of the beams entering the lens system. Focus on the bright green beams here. Those other small little beams are just reflections caused by inferior glass. Now notice how the beams change distance as I move that middle concave lens. Using a light bulb in place of lasers and an aperture on the final focusing lens to increase the sharpness, we can see this zoom lens in action. The demand for better and better lens systems for scientific discovery kept lens makers busy throughout the 17th and 18th century. But a coming era would really put lenses to the test, the era of photography. The very first lenses used for photography in the 19th century were single-element pieces of glass, just like in our science demonstration. But the problem is there's a lot of photographic issues from using just one lens, including chromatic aberration. That's where light of different wavelengths get bent differently as they pass through a lens. Anyone who wears glasses can see this effect when you look at a neon sign that has blue and red light. Just tilt your head up and down, you see the blue and red behaving differently. Spherical aberration, where not all light rays are converging at the same exact focal point. And coma aberration, where off-axis light smears and creates this comet-like tail. Now, these are just a few of the problems that image makers still have to deal with. The first widespread photographic process, the French-originated daguerreotype, used a lens by French lensmaker Charles Chevalier in 1839. Now, this lens was an achromatic doublet, cementing a biconvex element of crown glass with a biconcave element of flint glass. Now, these two types of glass have different properties, and combined, the lens greatly reduced chromatic aberration, leading to sharper images. This early lens used an aperture. That's a small hole that reduces the angle of light rays coming in, which also further increases the sharpness but reduces the amount of light available for the film. With an aperture of f16, and f-stop is a ratio of the lens focal length to the diameter of the aperture, this lens was very, very slow, taking 20 to 30 minutes for an outdoor daguerreotype exposure. Now, because of this limitation, this lens became known as the French landscape lens. For portraits, especially indoor portraits, a new type of lens configuration was needed. In 1840, the French Society for the Encouragement of National Industry offered an international prize for just such a thing. Joseph Petzval, a Slovakian mathematics professor with no background in optics, with the help of several human computers from the Austro-Hungarian army, took up the challenge and submitted his design in 1840, which would go on to be called the Petzval portrait lens. Now, this was a 4-element lens that had an aperture of f3.6, much faster than the landscape lens. A shaded outdoor sitting would only take a minute or two with the new wet collodion process for photography, and this lens could even expose an indoor portrait in about a minute. But Petzval didn't win the prize, mainly because he wasn't French. But his lens would go on to be the dominant design for nearly a century. It was sharp in the middle, but fell out of focus quickly on the sides, which gave portraits from the 1800s that soft edge halo focusing effect. And although Petzval lenses were mathematically devised lenses, lens makers would resort to just trial and error for the next 50 years, which included the first wide-angle Harrison and Schnitzer globe lens of 1862, and the Dallmeyer Rapid Rectal Linear UK and Stanheil Aplanat from 1866. These 4 lens types, the French landscape, the Petzval portrait, the globe, and the Rapid Rectal Linear Aplanat, were the 4 go-to lenses found in every 19th century photographer's bag. Heading into the 20th century, the story of lenses simply explode. We'll take a brief look at some few notable examples and some historical trends. Lens technology took a huge leap forward in 1890 with the release of the Zeiss Protar. For the first time since the Petzval portrait, we have a lens designed based on scientific formulas to reduce all lens aberrations, including astigmatism. Part of the key to success is the use of the new barium oxide crown glass, developed by Carl Zeiss's Jena Glass Works by Ernst Abbe and Otto Schott. This new Schott glass had a higher index of refraction, making it key to the development of better optics. So now, with better materials, the cat was out of the bag, and new designs for lenses flooded the marketplace. In 1893, Dennis Taylor, who was employed as chief engineer by T. Cook and Sons of York, patented the Cook triplet as a result of the new designs made possible by the invention of Schott crown glass. The triplet featured 3 elements, the center element being flint glass, while the other 2 being crown glass. The Cook triplet came to dominate the low-end industry, being used in modern projector lenses and binoculars, as well as some early motion picture lenses of the 20th century. But the folks at Zeiss weren't done yet. Paul Rudolph, working at Zeiss, patented the Tessar in 1902. Similar to the Cook triplet, it added 4th glass element, greatly improving performance. The Tessar design is still used in a lot of pancake-style lenses. As aberrations came under control with these new lens designs, attention turned on increasing the aperture size to allow for faster shooting. Ernemann Erno star in 1923 opened the aperture of an 85mm to an f2.0 and later to f1.8 in 1924, leading to a new era of photojournalism as less light was needed to expose an image. In 1926, Ernemann was absorbed by Zeiss, and the Erno star design was reworked and renamed Sonar. By 1932, a 50mm f1.5 was available. Another notable style of lens design was the double Gauss lens. Named after the mathematician Carl Friedrich Gauss, the double Gauss took what was originally an objective lens for a telescope and doubled it. The resulting lens has become the most intensely studied lens formula of the 20th century. The Gauss design greatly reduced optical flaws in almost every way, and these lenses could be made with very wide apertures and relatively inexpensively. Although the first commercially successful double Gauss, the Taylor, and Hobson Series 0, was released in 1920, there was a problem that prevented the double Gauss from really taking off, and that was reflection. A double Gauss needed at least 4 elements to work. Now, most modern designs have up to 8 elements to control aberration. Reflection, like the reflections we saw on that zoom lens laser demo, cuts down the amount of light that travels through the glass, reducing the lens's performance. The solution would come in an anti-reflective coating. Back in 1896, Dennis Taylor, working at Cooke, noticed something peculiar about older lenses. Glass that had been sitting around on the shelf for a long time took brighter pictures. This was due to the oxidation layer that had been building up over time that suppressed the reflection due to dispersion. By 1939, an artificial coating was developed at Zeiss to cut down the reflections as much as 66%. With this improvement, the double Gauss lens began to surpass the Sonar in terms of popularity. Hundreds of variations have been produced, and millions of these types of lenses sold. The common Nifty 50 Canon and Nikon 50mm lenses are based on the double Gauss design. Now, up to this time, we've been talking strictly about prime lenses with only one focal length. The variable focal length lens, the zoom lens, was first patented in 1902 by Clyde C. Allen. Called traveling vario or vero lens, they didn't see production for motion picture cameras until the late 20s, with the first use of a zoom shot was this one from 1927's It, starring Clara Bow. A motion picture film required less resolving power than stills film. An acceptably sharp zoom lens for still photography didn't come around until 1959 with the Voigtlander Zoomar 36 to 82 millimeter. So with all these lenses being designed and experimented with in the first half of the 20th century, an interesting shift occurred at the close of World War II. So far, we've been talking about European lens manufacturers, starting with the French, English, and finally German lenses, which include that powerhouse brand Zeiss. But in 1954, as part of a post-war economic recovery campaign, Japan began to seriously push quality lens production with manufacturer organizations Japan Machine Design Center, the JMDC, the Japan Camera Inspection Institute, JCII, banning the practice of copying foreign lens designs and the export of low-quality photographic equipment. They enforced this ban with a rigorous testing program that had to be passed before companies could ship orders overseas. By the 1960s, through a major industry push by the government, Japan's lens industry began to eclipse that of Germany in terms of quality and price. Many German brands began closing up shop and licensing their names to products to be manufactured in Southeast Asia. That also marks the end of naming lenses like Sonar or Tessar, as the Japanese much preferred using brand names and features codes to label their lenses. The quality control organizations ended in 1989, having completed their function. But as a result, when we talk about camera technology and lenses today, we almost exclusively talk about Japanese companies. I feel like we've only gotten a taste of the world of lenses. In the next video on lenses, we will focus on the properties of the modern day lens, the basics of what you're looking at when you put a lens on a camera. There's a lot of history and a lot of science to get us to where we are today. So go out there, use it, make something great. I'm John Hess, and I'll see you at filmmakeriq.com.